and for coming today.
Thanks for the kind introduction. I hope that I can live up to everything that you just said with the presentation today. But hi everyone. At least hi virtually. So today I'm going to talk about some of the work that we're doing at Cerebras, sort of in particular, kind of a survey not just of the work that I do, but kind of the different problems that we're solving at different parts of our software stack, and all the what I think are cool math problems that appear along the way. So kind of before we start, who are we? We being Cerebras Systems, we're yet another startup company in the Bay Area. There's no shortage of those, but we were founded in 2016 with the mission of transforming the computational landscape. Very common theme throughout, to both tackle that and to radically accelerate AI. But the approach that we're taking here, as opposed to some of the other places, is kind of a hardware-centric approach, and using this unique chip that we call the Wafer scale engine to do so. So we've been around now for 5 years now, with a mix of hardware, software, and ML research engineers, totaling, I say 250 there, but I think we're actually closer to 300 at this point. So what is it that we actually do? We build the Wafer scale engine. So this is the biggest computer chip in the world. And you might ask yourself, well, okay, so why build the biggest chip in the world? If we think about how we often build clusters and hardware for tackling, say, large problems, whether it's in scientific computing or in neural nets, because that's the hot thing going on right now. The way these chips are built, in case you don't know, is that you take a large circular silicon wafer, you etch your circuit directly onto it, and then you chop it up into individual pieces. So each little subrectangle here, in principle, becomes an individual chip. For example, some GPU or whatever processor you have. And then afterwards, when you get the chip, you surround it by a whole bunch of other hardware, you turn that into, say, a GPU, and then you work very hard on connecting them back, because we all know that one GPU is not going to be enough to run your massive neural net or whatever problem you have, which basically means you have taken a large piece of silicon, chopped it up, and then worked very hard to start putting it back together. And in the process, you're kind of losing a lot of your ability to move data around quickly. We sort of have come to the point today where when we're running these large problems, the slow part is not in the computation. The slow part is in moving the data around across your processors. So the idea behind the Wafer scale engine is, rather than take your big silicon or your big piece of silicon and chopping it up just to try and put it back together, don't chop it up, which basically results in what is the largest chip in the world. That banana is basically to scale of just pure silicon. What that means is that we have a single chip with roughly 400,000 processors, and all of the memory is directly on the chip. So, you might say 18 gigabytes of RAM, admittedly, for the largest problems, that might be somewhat limited, but this is purely static RAM. You only need one cycle on a given processor to access that information. So whenever you see, say, a GPU that has, say, 64 gigabytes of RAM, that's still dynamic RAM. There's still a memory hierarchy, and as opposed to just having everything right where your computation is. On top of that, because all the processors are sitting there on the silicon directly connected to each other in a mesh grid, the bandwidth is massive. So you can move data in an embarrassingly parallel way. If, say, I just wanted to move things left to right, I can move data across the entire column all at the same time. There's no bottleneck in this case. And so the nice thing is that we've been around for some time. This isn't just an idea that we're trying out. We actually have customers now. The idea of keeping everything on the chip, keeping reducing that bottleneck between moving around memory and computation is actually bearing fruit now. And we've partnered with national labs, and recently we've announced our first industry partner, GlaxoSmithKline. But by keeping all the computation on the actual chip, not moving things around between from the processor that's doing the work to some off-chip memory, we're achieving 50, 100-fold gains over a GPU, because everything is exactly where you need it if you set it up correctly. So with ANL, them running their cancer drug discovery problems, we've kept them happy, because as they've actually said, I don't think I have it on the slide, but it used to be that whenever they had to run their problems on GPUs, it would take them days. And by the time that their runs had finished, they would often forget what it is that they actually wanted to find out from that particular run. And now, rather than waiting a few days, after a couple hours, they get their answer and they can actually keep iterating quickly. But before we actually get to the whole neural net thing, we're here to radically transform the entire compute landscape. It's not just about neural nets. So before we even get to that, one thing that I do want to talk about that is near and dear to my heart, we've also applied to Krylov subspace methods. It's not just for neural nets. We have a massive chip that moves data around quickly. It's shaped like a matrix, so we can actually get huge gains for things like sparse iterative methods, and in the future for things like dense direct methods. So really, the goal here is, if you can put everything on the chip, you can organize your computation correctly, you can actually keep your processors busy all the time. And this could have massive ramifications on the way we decide to structure our parallel algorithms. So a little bit more detail in terms of how the chip is laid out. It is the big dinner plate of processors. The processors are arranged in what is roughly a 600 by 600 grid, or a 2D grid of processing elements, and they're connected. Adjacent processors are connected directly over silicon. So this basically means that in one clock cycle, any given processor can talk to its neighbor to the left, to the right, above, or below it. The other thing that we kind of want to understand about the way this thing works is that the hardware was really designed for a data flow execution model. So the idea is that rather than kind of trying to grab data from somewhere else, the hardware is set up so that when data arrives on the processor, it can automatically trigger and act on it. So that basically means if there's no data to work on, it doesn't have to do anything, or it could do other things that don't depend on the data. And as soon as data arrives, it will automatically wake up and act on it. And the other thing is that sparsity was sort of front and center in designing this chip as well. So the idea that, look, if you're, say, doing a nonlinearity like ReLU, or you're operating on sparse matrices, there's no point in transmitting zeros, nor is there a point in, say, multiplying on zeros. So we can actually send compressed representations that the hardware natively supports, and will just wake up on the non-zeros. So the core idea that we'll sort of see over and over again is the idea that we want to structure our programs to keep the computations local. So each processor is responsible for computing something, for doing some of the work, and the data is going to move. So the data is going to flow across the processors, waking up the processors to do something, and it'll keep going in that fashion. And that way, to the best of our ability, everyone stays busy. So let's talk about a first example where we could sort of apply this idea. As I said, something near and dear to my heart and my time at ICME, our work on, or another team's work on Krylov subspace methods. So as most of you probably know, especially given that I imagine you all went through 302, a Kernel subspace method is nothing but a sequence of sparse matrix vector products, some vector additions, some reductions across the vectors, and maybe some element-wise scaling. So we're basically going to use this exact idea that we're going to try to keep the operations in place. So every processor is going to be responsible for computing some piece of, say, the matrix vector output. And the vectors are going to be the things that flow across the processors. So you can imagine either the input vector is going to be moving between processors, waking them up in order to do the local multiplication. So the particular work that one of the teams at Cerebras was working on, they implemented a really high performance BiCG stab that was targeted for solving computational fluid dynamics problems. I'll admit it's a little bit of a simple problem in the sense that they took a three-dimensional cuboid regular mesh. So this is basically solving a PD on a 7-point stencil. And we have this two-dimensional grid of processors for a three-dimensional domain. You know, where in this case, our variables are going to be the points inside of the cuboid. The edges of the matrix area are going to correspond to the local interactions between the points. So we could literally just plop down the domain over which we're solving directly on the processors. So every processor is responsible for, say, a single point in X, Y, and all of the points in Z. And when you do the matrix vector product, the only processors you have to talk to are the ones that are directly adjacent to you, right? Because if you're a point sitting on this processor, in order to compute this point of your vector y, if you're doing a times x, well, you just need to talk to these guys that are adjacent to you. So here we have kind of the communication pattern across the chips. You could fully parallelize this. You know, everyone can just immediately send a point when it's ready. You only trigger when the data is there. If you're doing a reduction across the entire vector, say because you're computing the norm of the vector for the residual, it's embarrassingly parallel. You can basically have every processor send its local data to the left. So every row is happening totally in parallel, and then you can finally just perform the second part of the reduction going down. And again, you expose as much parallelism as possible. And the result of this is that we generate something that achieves 0.86 petaflops on a 500 million variable problem. You know, even if it is regular, that's still, in my opinion, relatively impressive. And even for such a large problem, every iteration of BiCG stab, so this is a non-symmetric, it's a method for solving non-symmetric sparse matrices. You need a multiplication with A and A transpose in every iteration, which is going to be the bulk of the work. We can achieve every iteration in 28 microseconds. And going along with this message of, you know, it's not just about how fast your processors are running, it's about how quickly you can move data so that they have something to act on. This implementation achieves 30% of the peak performance of the chip. Kind of the next best supercomputer achieves only 3% because they're bogged down moving data around. Whereas here, you know, this is perfectly spread out for this type of problem. So there's really no waiting in between operations. And, you know, just because this is an industry talk, we have to compare against competitors. You know, this is maybe somewhat unfair to compare against a single GPU node, but it is 10,000x bigger than that. But maybe more impressive, you know, compared to any other CPU cluster that has run on this problem, their implementation was 200x faster. And so the rest of this talk is going to be about deep neural nets, but the idea is still the same. We're going to be kind of walking through the different stages of our compilation stack to try and figure out, well, what problems do we have to solve to kind of really expose this idea of we want to keep the computations local, and we want to move the data around as efficiently as possible. Maybe this is a place to stop for a couple questions that I see in the chat.
Sure, it looks like there are two, Ron. The first is on what do you mean by automatically wake up? And can you give an example of another architecture where the processor does not automatically wake up?
So the idea is that there's hardware support for these things, like these threads. You can think of them as basically threads that wake up upon receiving data on a certain channel. So basically, let's say you're doing a matrix vector product, you're streaming in elements of X. Rather than sort of blocking and waiting until you receive X in order to do something where you could be doing other things, the processors can be doing whatever, and upon receiving some element that they need to perform the multiplication on, it'll automatically trigger that task. So you don't need to poll or anything. You don't need to have any blocking tasks. It'll just it'll trigger on that data. And then I see there's a question about hardware support for sparse data. The idea is that there's a representation for, say, sparse vectors where you're sending pairs of data in each wavelet is a data index pair. And on top of that, when you're, say, doing these very common operations, the hardware will automatically sort of pick the correct index in memory to act on. So if we'll have an example of this later, but the idea is if you're sending a data, you have the wavelet value 1.5 index 3. When you're say doing a matrix vector product, you need to hit the third column of your matrix. The hardware will automatically pick out that third column rather than, say, waste cycles on doing the index calculation and then picking out the value. And I see one more question. Unstructured mesh. So this is something that we're working on. This was definitely a simpler example where we're taking a perfect 3D mesh and just plopping it down onto a 2D domain. To do it on a unstructured mesh, obviously you're not going to get as good performance, and it's really about, it becomes a domain decomposition problem in terms of trying to find the parts of your domain where you don't have to communicate too much across like too many people, but in the worst case, it'll have to suffer. And then from Gianluca, so if it's larger or smaller, so if, say, it is smaller and the answer is it depends. If you increase Z dramatically using the same sort of distribution, you will necessarily suffer. So you may want to kind of permute the directions of your domain so that the number of points on any given processor is not too many, while at the same time, the 600 by 600 is nice because that roughly corresponds to the number of processors in the domain. In principle, I think they had some simulations where it should scale roughly linearly as long as you're not getting too many, as long as you're not clogging the pipes when transmitting data. But I think it was fairly close to linear as they bumped up the problem size. Okay, moving on then. So what do we do for neural nets? As I said, the idea is very similar. Let's say we have this kind of simplistic linear graph going on. So each node there is some sort of operation, or say you can think of it as a layer, fully connected layer, convolution layer, nonlinearity, whatever. We're going to take the layer, we're going to assign some processors to perform that computation on the chip. And that's all that chip is going to, or that's all those processors are going to do. We're going to take the second layer, we're going to plop that down, and ideally close. And then we're going to take the third layer and plop it down. And we're going to continue in this way to try and tile the entire graph, or the entire computational graph, onto the wafer scale engine. So the idea here is each one of these nodes here corresponds to some region of the fabric. Then we're gonna route the edges of the rectangles between each other. So ideally, since these two nodes are adjacent to each other, they'll be in adjacent regions of the fabric. We're gonna set up the routes between the two rectangles to sort of automatically feed data. So in some sense, you can think of this as we are configuring pipes and you're just flowing water through them. And once we've set this up, we're just going to start continuously streaming input. And if you do this correctly, all of your processors are going to be busy at the same time in this pipelined execution. So the idea is, at any given step, any one of these rectangles is going to be performing some sort of computation on a different point in your input. As you notice, like, the sizes of these rectangles are different. The idea being that, let's think about this layer. This probably corresponds to some sort of large computation that takes up a lot of time. Therefore, we break it up among a lot of processors versus, say, this one, which is going to be faster. And the idea is, if the amount of time to process any given activation is roughly the same across all the kernels, the entire pipeline stays busy, right? So the time it takes to flow the input activation to the output activation across this layer should be roughly the same as in this layer, that layer, and so on, which means at any given time, everyone is busy processing at least some piece of the input. And then we can very quickly tell whether a picture is a dog or a cat, because that's always the example used by everyone. So kind of from a 30,000-foot view of what's going on, we're going to think of the deep neural net as some sort of computational graph. So that means that each layer is going to be, or say each operation is going to be a node in this graph. And when I say operation, I'm thinking kind of the basic things like a matrix vector product, the convolution, a reduction, a broadcast operation. The edges in this graph are going to be the tensors. And by tensors, I just mean, some square or cuboid of data, which is either, say, the training data, the output, the activations, maybe gradients, or the weights that you're training on. And what we're going to think of as the layers, which correspond in our terminology in the company to kernels, are subgraphs in this computational graph. So you can think of this as the FC layer, which in itself is composed of usually, say, 4 operations, where you have the forward pass, so a matrix vector product, the backwards pass, which is the transpose, computing the gradient, and updating the weights. And so we're going to group those things into what eventually becomes a single kernel. We'll have some highly optimized implementation for that layer. And then we're going to place that kernel onto the fabric. So each one of these subgraphs eventually becomes a rectangle of processors on the chips. And then, as we sort of saw, the data is we're going to configure the pipes to route the data through the rectangles between each other. And as you can imagine, the way we're going to decide how many processors in what shape and where to place them is really all about maximizing the bandwidth going through. And, the goal is to just feed the beast, keep the machine busy, make sure that all the processors can be doing something at some time. So all of this sort of leads to what we call the Cerebrus graph compiler. So this is the thing that takes some sort of, say, customer model written in TensorFlow or PyTorch or whatever, and then turns it into an executable that will actually run on the chip. So to some degree, the entire software team. So everyone who isn't in the ML research or hardware team is working on the compiler to solve a bunch of problems that go from something that the customer is going to write to something that will actually run. So the rough steps, and we'll sort of go into more detail with them throughout this talk. Step one, we're going to want to extract whatever the customer wrote into our own internal graph representation that we'll sort of use as the input for the rest of the stack. Then we're going to run something called kernel matching, where the idea is, look, I have this unstructured computational graph. Let's find the operations that we know how to do in it. So let's find the thing that corresponds to the FC layer, the convolution layer, the softmax or whatever. And by finding those, we'll grab our efficient implementations that the kernel writers have written, and then we're going to run place and route. So we know what each kernel is doing. Let's assign pieces of the fabric to each of those kernels, configure the pipes, and then compile the source code and let it run. So as I sort of said, this whole compilation is going to be broken down into stages. And we'll sort of see almost each one of these stages is going to try to approximate or solve some sort of NP-hard problem. So we'll see examples of graph isomorphism, knapsack problems, all kinds of black box optimization that we have to solve. So, maybe this is another chance to answer some quick questions, but the rest of the talk is really just going to be going into a few of those stages and talking about, look at how hard this problem is, and maybe we can solve it. Or at the very least, apparently we could, to the level that we've made some customers happy. So looking at the questions, are the sizes of the neural net layers and the number of neural net layers fixed when you fabricate the chip? So the chip is the chip is just the chip. This is part of how we configure what each processor is going to do in software. So when we fabricate the chip, there's no notion that it's really going to be used for the neural net layer. This configuration is all just part of this compilation stack. So starting from here, it's just a matter of how do we decide what to tell each processor to do. How large of the streaming input could the Wafer chip support up to? I mean, in theory, infinite, but in terms of any reasonable, the bandwidth through the chip is at the petabit level. So it could reasonably support, a large amount of streaming data, even if the amount of data that could actually sit on the chip at any given time is limited to 18 gigabytes. There's a question about no global clock. So on a given die, so you saw that this big square was subdivided into a bunch of little rectangles. They are actually all synchronized together, and across dies they are almost synchronized to within one clock cycle. So you could still pretend that there's a notion of a global clock. How quickly can you produce? All right, so how do you ensure that compilation steps produce an executable that exactly reproduces the original intent of the code? As any compiler, we have to kind of make sure that stage to stage, even though we've changed the representation, we haven't changed what the code actually means. And if it doesn't, then that is the fault of the programmers that wrote the compiler. How quickly can we produce an executable? Depends on the problem, and you guys will see why soon. I mean, smaller problems, a couple minutes, it could take up to a couple hours for, say, a very big neural network that is heavily constrained. All right, step one, kernel matching. We have some computational graph that we've translated from TensorFlow, and our goal is to turn it into, or to figure out which operations sort of belong together and exist in our kernel library. So as you can imagine, I've taken some random graph here, created some random clustering for illustration purposes, but we've already sort of hit our first NP-hard problem, or theoretically NP-hard problem, of look, this is an unstructured graph, and I want to figure out which of these operations correspond to a known subgraph that is, say, my FC layer or my convolution layer. And worse yet, it's not just that I'm doing, say, graph isomorphism, because these are small graphs, so whatever, 5 nodes is not that hard to figure out whether you've matched it there. But it's also a graph tiling problem, because in some sense, we want to cover the entire graph in these known subgraphs, and you may have overlapping portions, or depending on which parts you decide to match first, you may or may not be able to match the rest of the graph. And even if, say, you could match the entire graph, there are many tilings that are possible and will have different ramifications, because different tilings means you've converted your graph into different kernel graphs. So rather than, say, you have the choice of, say, taking the FC and taking the nonlinearity separately, or of fusing them. But by fusing them this way, you may not have been able to fuse the nonlinearity with, say, another graph, which possibly could have been more efficient. So already this is some sort of fairly difficult problem that we can talk a little bit about at the end in terms of how we actually solve it. But this already gives a flavor of, we've hit a big graph problem that we have to solve. Worse yet, we might not actually be able to match the entire graph to known kernels. And we'll talk a little bit later about what we do in that case. But let's suppose that we've solved the problem of figuring out the graph tiling. We know what kernels we want to implement. So now we have our kernel team, which goes and writes super duper highly optimized code for these common operations. So for example, your FC, which appears all the time, softmax, things that customers constantly want. Our kernel writers go and write these extremely parallelized algorithms targeted for our hardware using the hardware constructs that we have to squeeze out every last bit of performance from the architecture. As you can imagine, the programming model is quite different here. It's not, say, like a GPU where you've got a warp that where everyone's going to be doing the same operation. You're going to load the data and try to make sure that it's all coalesced. The programming model here is kind of controlled anarchy. All the processors are just doing stuff whenever they can. There's no MPI join or anything like that where you can synchronize all of them. The synchronization happens when you kind of try to send data to someone who may or may not be ready to receive it, and or you try to wait on data that you receive, and you just kind of try to set up your control flow graph to make sure that if you're waiting, you can do other stuff. Things will automatically trigger for you when it's ready, and you reduce the number of bubbles. So it's a very different way to think about data arriving and forcing you to do something, as opposed to trying to grab data whenever you want to do a particular computation. So one example I want to sort of go through here kind of quickly is how we might think of doing a matrix vector product in this model. The way we typically learned matrix vector products, you're going to have your matrix, you're going to take a row of it, you're going to do the dot product with the input vector, and that's going to give you one element of your output. And you can sort of trivially parallelize this if you were to, say, move the matrix through across the processors. But there's kind of two main problems here. Well, one is we're typically thinking of streaming the vector as opposed to the matrix, because that corresponds to, say, our training data. And the other thing is it's kind of bad reuse of information here, because every one element of the matrix is only going to hit one element of the input vector. If we think about the outer product approach, let's say I'm streaming X now, I can stream one element of X. It's going to hit an entire column of W, and I can update the entire output with the scaling of this column, and then totally forget about X. It's truly this streaming approach. And similarly, I could just keep streaming the rest of X in this fire and forget fashion. So if I were going to distribute this, we exactly follow this idea. Let's chunk up our matrix into the individual processors. We're going to let X stream from the top, which basically means that every processor can totally independently just compute its own local output without depending on anyone else. And then we could just flow that local output across in a perpendicular direction to compute the final result and keep the streaming going. So if I were to say join this with another MATVEX sitting here, the data is already perfectly laid out to keep this going. And as I said before, the hardware natively supports sparse tensors. So if in this case, X was sparse, you can think of, well, if this was 0 and this was 0, I'm not actually going to send this data. Whoever produced it will probably not have sent me a 0. So really, I'm going to send just this element. The amount of time I spent computing that little piece of the output is going to be significantly faster because I'm not acting on zeros, nor am I clogging the pipes with sending zeros. This is, of course, also a relatively simple example. In general, parallel programming is hard even on this model because we have kind of a lot of competing goals. You want to make sure that however you're distributing the data, you don't clog up the communication channels. As I can imagine, many of you have sat in traffic where, for example, you've hit congestion because everyone tries to go in at once. You get those phantom jams. And so everything kind of bunches up together and you have this bubble of no movement that's flowing backwards. And the exact same thing can happen here if you don't distribute your work in a proper way. However, in order to kind of avoid those things, you may try to buffer or something like that. But as you can imagine, every processor has limited resources. There is no shared memory in this case. Every processor has only its local memory, which means you can try to do some buffering, but you can only do so much before you're forced to get rid of that data by actually acting on it, which means that if you take a long time to process any given piece of any, say, data wavelet, none of the other data wavelets that are stuck will be able to go through. As you can imagine, how you distribute the data really matters. There's probably going to be some optimal way in which you want to distribute the work, and there's going to be some way in which you're going to receive the data. So everyone has to make the trade-offs of, well, do we want to waste time reshuffling the data? How quickly can we reshuffle the data? Or do we simply accept that we're going to use it the way we received it and take the penalty in the computation? So for any given kernel, you can imagine convolutions have a massive number of implementations that you can take that will have all kinds of different trade-offs depending on the aspect ratio of your image or the number of channels and so on. So kind of the optimal implementation is very much an open problem. But let's pretend that some God-given kernel has been written for you. You have a way to implement in source code. Next stage is going to be to place it onto the graph. So this is basically the idea of, okay, look, we know what our kernels are going to be. We're going to assign each one to a rectangle on the fabric. How do we do this? And here's sort of an example of a realistic placement that isn't a cartoon where we perfectly tile the fabric, where, this may not actually be the optimal thing because, as you can imagine, this is a very difficult problem. It's a large black box optimization problem with many competing objectives. Because for a given kernel, you may want to assign it more processors to make it more efficient. However, you only have so much space on the fabric. On top of that, the relative number of processors that you may want to assign between any two kernels really depends on how heavy the computation is for those two kernels. So you want to make sure that the amount of time to process a given, say, piece of training data is going to be the same between two kernels to make sure that you never have dead time. If one takes much longer to process than another, the faster one's just going to be waiting for the slower one to produce data for it or to be able to accept the data that it's produced. On top of that, so given that this happens before we actually assign the routes, the placer has to be aware of the routes. But beyond even that, when we try to place things onto the chip, every kernel is going to have different constraints for what it can do. There's no real closed form way to express this, because it may only accept certain data distributions or only support certain sizes. And even if this wasn't all a problem, there's just a huge number of degrees of freedom. Like there's the rectangle size, the orientation of the rectangle, the location of it. Not only do you want to, give it the appropriate size, you want to make sure that communicating kernels are going to be close to each other and that they're facing the correct way. This, to Gianluca's previous question of how long does compilation take, this stage could take, say, upwards of an hour. This stage is really multiple stages, but it could take up to an hour or two if you, say, have a lot of kernels that you have to place, and there's a lot of flexibility in terms of what these kernels support. So as I sort of said, this is a big black box optimization problem. Each kernel, and the reason for this is because what each kernel can do really depends on the kernel. There's hardly a kind of a shared approach between them. And so just to give a flavor on how we actually try to solve this, the idea is that like any black box optimization problem, the placer, which is the thing that's actually doing the placement, is gonna query the kernels to say, hey, like, what do you support? Tell me how many processors you want. And if I give this to you, how fast are you gonna be? And after it does this, it checks, all right, are any of you guys gonna blow your memory budget if you do that? Because every processor can only support so much. So it's this whole iterative dance of trying to propose some sort of layout or some sort of floor plan, seeing whether it works, iterating on this until we can find at least some sort of feasible solution, and ideally one that's sort of optimal in the sense of it minimizes or it maximizes the throughput by making sure that the maximum time that any one kernel has to take is as small as possible. Some additional wrinkles on top of this is the fact that not only do we have to allocate space for each kernel, but we may also have to allocate space for buffers. So as you can imagine, let's suppose we have ResNet or something, so we have a skip connection. Things are usually not as nice as just having a linear sequence of operations. If this node produces some tensor that's going to be used by both these two nodes, this node can't do anything until it has received input from this predecessor too, which basically means that we have to be able to save the intermediate value here so that this guy is also not blocked on being able to process the next piece of training data. So the way, just to give a little bit of flavor on how we solve that one, this actually gets modeled as an integer linear program. But the annoying part is that these buffers are themselves placeable, which then also have to be, they have to be part of the placer, because if you want to overlap the buffer code with, say, a kernel, you have to, again, make sure that the amount of memory that you're using will actually fit on any given processor. Now, they've been exploring with using reinforcement learning to actually solve this. Right now, there's a simulated annealing algorithm that's being used, but over time, as they're solving more and more things and seeing this, you can sort of imagine that you can use a reinforcement learning approach. So it's just kind of funny. It's turtles all the way down, and that we're using machine learning to try and run some machine learning problem. All right, last stage before we take a break from this stuff. So let's suppose that somehow we have found a valid floor plan. Now the question is, how do we connect the different rectangles together on the chip? So any given processor can talk to its neighbors. There's a notion of colors on the processors, which basically just means there are different channels over which you can send data. So even though there's only one physical wire over which you can send data, the idea is if I have to send two tensors in the same direction, the colors are the way by which I can disambiguate what one tensor is from the other. So obviously, if you're sending some two different tensors across the same processor, they have to be over different channels. So now the question is, well, what colors do you give to each of these channels? What directions should they flow? And so we go from this floor plan that hasn't actually assigned in which direction everything is going to, kind of a large constraint problem to make sure that two kernels, you can set up routes between two kernels that need to talk to each other while at the same time making sure there are no clashes, because these routes are obviously going to be crossing all over the place, to make sure that you're never confused about which piece of data means what. And so this sort of ends this whole slew of let's get a flavor of the different kinds of optimization problems and computational math problems that we have to solve. There's really more that are happening under the hood, especially within placement itself. It is really just a whole slew of a bunch of sequential problems that we may or may not be solving in the correct order even. But let's take a quick break right here to answer a couple of questions, and then we'll talk about the very serious problem that I have ignored up until this point. All right. Let's see, on slide 20, what is the difference between the orange and green rectangles? Let's find out. There's no difference. That's just an artifact of the visualizer. Is there a specific server hosting the wafer chips? So the thing we actually sell is basically the entire system. So it's basically a box the size of a small server rack, which contains a single one of these wafer scale engines. So it does all the power for it, the cooling, the IO, because all from the algorithmic point of view, there's all these novel things that we have to do in order to run things on the chip. But I've totally ignored the hardware breakthroughs they've had to make to power the chip, make sure the chip is so big that it could crack if you don't make sure that processor work is somewhat balanced, because if different parts of it heat up as they're running things, the thermal expansion coefficient will actually cause them to break, because some parts of it will will expand from the heat while others won't. So it is very much like we build the entire box within the company that runs this thing, and don't just give them the dinner plate that is the chip and tell them to hook it up themselves. If the application has an overall small footprint on the wafer, is there a chance to pipe a second independent application? So that is something that we're working on, where basically running multiple models at the same time. So if it is a small model, there's no reason you can't run multiple models at the same time. Fundamentally, the idea is the same, you just consider it on a smaller fabric. How easy is it for a user to develop their code for the wafer scale processor? Based on my understanding, it sounds like some of the stages you described would need a specialized team to be done correctly. Absolutely, it is not easy. We are working on the idea of how do we make it easier for users to program this thing. Let's say even ignoring the stages, but just to write the kernel code itself is something that we're continuously thinking on and kind of expanding. So when I first started, almost the only thing that people were writing in was in assembly code directly. We're expanding the languages to go beyond that, because it is a nightmare to have to write at such a low level. In fact, the thing that I'm going to talk about next is also in some ways can be seen as the push of how do we make it easier for users to be able to write their code so that they're not just stuck writing TensorFlow only and kind of praying to us that it'll work, but they can actually have some way to influence the success of compilation. All right, so what is this serious thing that we've ignored? We basically said, all right, if we can match the entire computational graph to these individual kernels, then life is good, or at least good in the sense that we know what steps we have to solve after. However, what if there are unmatched operations that are in the graph? So things that appear that we can't even match to some kernel that we have code for. Basically that's already sounds like a non-starter. Now, fortunately, that does not mean the CS1 will actually catch fire. This is the team that I work on. We call the distributed task generator. And the idea is that we're going to automatically generate kernels from the computational graph directly. So let's say you have some like weird tensor contractions or like weird nonlinearities that we don't have in our kernel library that some expert kernel programmer has written for us. Well, we can't just fail for the customer and do nothing. We're going to automatically generate code on the fly. So the idea is we take some computational graph for which we don't know a priori how to generate code for it, and we're going to generate code for it on the fly. This is our compiler that will automatically generate kernel layouts, do everything that that a kernel writer would have done, knowing like exactly what operation they're doing, except with zero human intervention. So kind of the ultimate goal is to get them all fired, make myself obsolete. Probably never happened, but that is the ultimate goal here, that we fully take the human out of the equation to make sure that we can handle basically everything that is expressible in the computational graph. So the way that we sort of approach this, there's kind of three major components to this. Step one, we've received some sort of big unmatched graph, and we run something called the kernelizer, where the idea is, well, we're not going to consider the entire unmatched graph as a single kernel. Let's break it up into individual pieces that will themselves each become what we call an autogen kernel or an auto-generated kernel. This is, you can think of sort of like kernel matching, except the goals are slightly different, where we don't really know what particular operations we're looking for, but we may want to say minimize the IO bandwidth between different kernels, or we want to be aware of kind of buffer allocation to try and minimize that. But the goal of this stage is break things up into individual kernels that we will later instantiate. Then step two, sort of called actually creating the autogen kernel, we got to figure out our implementation on the fly. So as you can imagine, if I received something that is a matvec, but I don't actually know is a matvec, how do I automatically discover that, well, I want to have X come in from the top, Y go out perpendicularly and break W up, sort of as we saw before, or worse yet, if it's, say, a convolution or some totally random tensor contraction. The goal here is figure out, all right, how do I actually break up this work in a prototypical way and do all the stack negotiations if I were a handwritten kernel that actually knew what I was doing. And this is basically means solving some sort of big feasibility problem to try and make sure that for any given processor, the data is going to be flowing across it. All the data that it needs will eventually be visible. And without kind of doing arbitrary data redistribution, which A, would be expensive, and B, is in itself a very difficult problem that we would have to solve. And then the last step is, once we know how we want to implement the kernel, let's say we know that we want X coming in from the top and Y going out on the left, and each processor is going to do some amount of the work, we're going to automatically generate some microcode. So the thing that the kernel writer would have done, we're just going to go have the compiler generated on its own. So in the previous step, we've basically figured out, all right, here's how many processors we're getting in which shape, which directions all the tensors are going, who's doing what. Go and actually generate the C-like source code to actually run the kernel. And you could also sort of imagine, if we just take step 3 on its own, it gives us a way to say, if a customer says, look, I want to generate a kernel that breaks up the work in this way, but I don't want to have to go and write the nitty-gritty source code, doing all the register allocation and like writing all the microcode instructions. You know, this automatic code generator could basically do that. You tell it a high-level description of, here's how I want to do my convolution, and it'll program the processors for you to do it in exactly that way. So just a little bit about how we do that. Back at CME, I was doing a lot of numerical linear algebra with real numbers. Here we're basically doing a bunch of linear algebra with integers. So we kind of represent everything using integer lattices with constraints on them. By quasi-affine constraints, they're basically just affine constraints, but you're also allowed to take the floors or take mods of stuff. And we represent the operations we want to do in this language. So for example, if I wanted to distribute, say, a matrix or the work for doing a matvec, so the, our favorite two-dimensional loop here, I could say, all right, W has two indices. I goes from 0 to 31, J goes from 0 to 15. PE here stands for processing element. So the idea is a given index or a given element of the matrix W will land on processor where I is divided by 8 and J is divided by 4. So we're literally blocking up W as we saw before, where each processor is going to receive an 8x4 submatrix, and consequently also each processor is going to be responsible for performing an 8x4 matrix vector product.
And Ron, I just want to jump in. We're at the 5 o'clock hour now. So I know some people have to jump off, but maybe if you want to wrap it up in a minute or so.
This is the last slide. Yeah.
Okay.
So really, we're just going to be reasoning about the relationship between tensor indices. So we don't really care what the operation is, just which elements interact together, which means we have to solve some sort of feasibility problem that everyone that needs to interact does interact. We're going to generate, the idea is we break up all of these computations into motifs. So if I'm trying to send data out, it doesn't matter how I computed that data. What matters is which direction things are going, and do they need to be collected together like a reduction, or do we say serialize them out where they all kind of orchestrate this dance of flowing through each other? And we combine all these building blocks together to hopefully generate functionally correct code. So just to wrap up, as you can see, the computational math background is essential for every level of the stack around here. We're going to need all those expert parallel programmers that are writing highly efficient code for targeting our architecture. We have so many optimization problems that are being solved to like questionable optimality. So having a good background in that is going to be a huge help to either be able to land larger networks or improve the performance of our existing ones. Performance modeling, especially for these kind of complicated parallel programming or parallel kernels, is essential to make sure that what you think you're going to get is what you're actually going to get. Otherwise, you're going to get stalls and bubbles. And, these are big coupled problems. How do we sequentialize them? How do we, we can't just ask the placer to solve everything in one step. That's way too big a problem. How do we break it up into sub problems that make sense to solve in order? So all kinds of things throughout the entire company to work on. So, those are interested, please feel free to ask questions. Yeah, I can let you guys know about some of our approaches to things, some of the other problems that we're working on. And otherwise, thank you.
Thanks, Ron. That's fantastic. Really appreciate you sharing all the exciting things you're working on and the challenges. Given the timing, I guess we'll let people follow up with you directly with your email here. But really appreciate you coming. And we'll also have this taped, everyone, if you want to catch it in more detail afterwards. We'll send out that link soon.
But Ron, maybe you do want to answer the question that is in the chat now. How many ICME are Cerebras? That's an interesting question.
So let me just quickly count. On my team alone, there's 4 on my team, plus at least 3 others in a different team, and 2 more that are going to be joining soon. So we're up to 9. Unless I've missed someone. Plus we're getting an intern, so we'll count it as 10.
Fantastic.
Impressive.
That is really great. Well, good luck with everything there. And thanks again for today. That was an excellent talk.
Thanks.
Thank you, Ron.
All right.
Bye, everyone.
Bye, everyone.
And see you next week. PayPal will be speaking to directors there on data science and AI applications.